have the honor to close things here. So I don't have the slides. I'm going to do my best so that you understand what I'm talking about. Always when I start with a new type of topic, I'd like everyone in the room, doesn't matter your background or your particular culture, to understand what I'm talking about and that we have all the same understanding. The first 10 minutes, because the topic is bringing physical AI into practice, I'd like then to elaborate on how I've done that the first 23 years of my working life. And this last 10 minutes is also to elaborate on how we're doing it now with my company, also for the next 23 years in the future, but also why we need everyone in this room to be able then to support us, and I'll get into that. So you already heard that I come from the automotive industry. So if you've driven a BMW, any car from the Volkswagen Group, a Ford, or from Stellantis, all of you have driven my software and the software I've created with my teams. So how did I got into that? Well, I was 10 years old watching Knight Rider. I don't know, there's also young people here, but I think everybody knows that. And I fell in love with KITT. And I told my father, I want to be an inventor of intelligent machines. I didn't know the term engineer at the time. I have no clue what a data scientist was, and I was 10 years old. So I embarked myself first on studying machine learning, and I was the first female software engineer at the BMW Group. And I'm never going to forget, I was in a room just as big as here, and they brought me in because their E60, the 2004 model of the Pfeiffer, was having a lot of problems. They had an entire, what would be a parking lot in what would be one of their major plants, full of cars that didn't work. They would have hundreds, if not dozens, of engineers from R&D going there with the laptops, having to reinstall the software, we call it flashing in automotive jargon, to try to find what the problems were, which was trying to find a needle in a haystack. So then they brought 26-year-old me, young blonde girl, talked to 200 male engineers. What do I know about cars? And I was explaining them, we need to solve the particular problem, 80% natural intelligence in the form of structure, processes, collaboration, a culture of growth, a culture of accepting errors, as well as sober investment in R&D, and as well along the chain. So everyone immediately, you can see their reaction was, we make cars here, not processes. Everyone yelled at me that. And because I knew they were going to do that, I created a presentation with a simulation, but I first created their map. I made an architecture of something very simple, the signal of a wheel speed sensor. And that signal, I showed them, from the raw signal, the different noise was transformed into 70 different software-based signals going into 40 of their ECU controllers for the different functionals of the car. And then I created an exponential tree showing them the cascading amount of applications that would fail if those 17 signals were wrong. And then I asked them, okay, you all tell me you know how to make cars and you don't need process, structure, systems engineering. Who in this room can explain me why the car, all the vehicles in the entire signal, and Mr. Mettner is also laughing, he knows that, in the entire signal list needs 17 different speed signals. And who do you think raised their hand and could answer me my question? Nobody. And then that was a time in which they looked and say, okay, we're going to listen. The BMW Group gave me a team of 17 external people from IBM, from external consultings, and access to the whole of the R&D to create what was called the system orientation project to bring systems engineering and systems of systems, what you were addressing, thinking outside of the car. So the car is a system, outside of the car is the people, the semaphores, other cars, and to bring an understanding, first functionality, what do we want to do before technology? And understanding that it is a task so complex, no person can do it alone. So that's why from having what we call silo wars between departments, it became a cultural transformation, before technological transformation, a cultural transformation. We have to lead and change everyone to understand what systems engineering was. And that's why I trained everybody. I trained all my peers, managers, all the way to what would be CEO from the particular area where I was, that was electronics, to understand what systems engineering was, what collaboration was, why we needed a culture of growth, and why we needed to bring that particular aspect before changing one line of code. Then they said, okay, well, everything what was done was established, and I had the idea of creating the so-called integration steps, which came from how we do iterative software engineering, just incrementally. Start small and start integrating everything, because that was one of the challenges, and I know you've heard that a lot. And then they say, well, let's do automatic drive. What do we need in order to have that? And I say, well, we need the equivalent of an intelligence system of the car. So we need a central computer similar to a human brain to be able to establish and understand, and we need a measuring tape. So how do we know when an auto steer is dangerous or a sudden brake in the car is dangerous? How do we teach the car to have the same cognitive abilities as a human to understand traffic, to understand a traffic light? We needed to work with other automotive OEMs. So imagine, revolution. Yeah, so a lot of politics involved. And 18 months later, we established the first group of initiative of automotive creators for software, German HIS, yeah, Herstellerinitiative Software, to create that standard. And then we went to the VDA in order to establish what are the dangers of an auto steer or the braking system, to create and know what are the particular physical forces that need to be validated before the car has the chance to be given the freedom to make a decision like a human. Shall I accelerate, shall I brake, or shall I steer? So from there, that's where your ACC stop and go that you have in your car comes from. So several years on that working group. And then it came that I still wanted to create a kit. So I moved to Mercedes-Benz, where they gave me the research team to create what was called autonomous driving in the factory. And we did all the systems and safety analysis, and we figured out we didn't have a standard for that. So we needed to create that one. We needed to create a lobby. We needed to explain people what was an autonomous driving car. And what was the limitation? The limitation was we needed to talk to the German government and explain them first what that was. But how many politicians in the German government understand systems engineering or artificial intelligence? So we first have to do, again, start the same strategy, awareness, training, and being able then to come and find the right partners. So 2.5 years later, we had what was called the first definition, and we wanted to have just from level 0, that means no assistance, 1 and 2, which is your typical ADAS that you have in your car, to 3, 2 autonomous driving, for example, the autonomous chauffeur that you can find at Mercedes-Benz or Waymo, and then 4, which is having the same equivalent as a human, and 5 is an intelligent car-like kit, which we still don't have. And we only have 3, because a judge told me we cannot give humans the level 4, because humans will get scared if a car would be driving alone by itself. So it created a tremendous bureaucracy in Germany. So for practical implementation, I figure out, well, is 80% natural intelligence and 20% technology, but the limitation is 80% natural stupidity and 20% artificial stupidity. Software hardware errors that people love to call now hallucinations. So how do we bring about and try to fix that? And I came up with the idea and with the team that we needed to have from a German collaboration to a European collaboration and also go across the pond. Yeah? We needed to bring this to OIGA. So we started actually those working groups, in order then to establish and start to create that technology. That means we didn't have the hardware, we didn't have the software, and we didn't have what would be the teams to do that. That means we needed to go to universities and tell them you have to bring machine learning, systems engineering into the particular typical engineering type of programs. And German universities are a bit, as we say, German consultants resistance. So we went across the pond, and we went also to the UK, and there is where we found some ear. So that's another, let's say, cultural, we spoke a lot about here about cultural limitations. But then, yes, we had our autonomous driving in the factory, but I told them we cannot bring this on the street, it's not safe enough. Yeah? And safe enough is already was mentioned. When do you accept that a robot is safe for there? The human acceptance is a robot should have 0 failures, 0 faults. Should always come into the safe state. Should always stop and keep a human safe in a particular state. So how could we do it with the technology there that was made for what we call ACLD, so 10 minus 8. That means from 1 million property buildings per year, 10 were allowed, or 100 were allowed to fail, depending on the particular system. So that is 100 cars or 10 cars, our company would get sued in the United States, and you have no idea how those areas are. You get an engineer from NASA that looks at your entire code, does their engineering of your system and tells you, this is particularly the area that affected the particular victim, and then the other lawyer comes and says, well, that is what killed this poor person, and that's why you're losing here. So that means that the state of the art in science simply wasn't ready. We needed to come back and say we need R&D. So how do we get grants from the government? Going back to politicians and say we need grants, we need to create a Pegasus project, we need again new talent, etc. Long story short, we did that. And then we created the first autonomous car, and that was when I moved to the Volkswagen Group with Audi. And that was the first time we had a car that was level 4, that could decide like a human, that could understand everything that's happening on the road, and my task was in different, what would be weather conditions, because that was the limit. Yeah? Teslas, that's not a level 3, level 4 car, it's an ADAS system, because a true level 4 car had to be completely brand new. And how do you make something new that didn't exist before? You have to think out of the box. So we have to ensure that the car had redundant braking systems, redundant steering systems, redundant powertrain systems, new types of hardware materials to ensure they didn't get too heavy. If not, it wouldn't be allowed on the road. It couldn't be so fast. You cannot use it for the Autobahn, to drive at 250. And it had to be a particular content and context for understanding. That means we had to become all data scientists, data engineers, to learn how to create quality data for the algorithms to transform it in the models. And that's why I go into my definition of what AI is. AI, to completely make it and unromanticize it, is applied mathematics in the form of algorithms in a particular IT infrastructure, hardware, electric, electronic, mechanical, needing a particular energy source. That's it. AI is exactly that. So that's why I'm very, very skeptical when someone says AGI. Well, let's first define what intelligence is. And that means we're saying, and the particulars that I like to refer is that artificial intelligence is the ability of an artificial technology system to mimic human cognition, so cognitive intelligence and memorial intelligence. We have 4. Yeah? We also have emotional intelligence, and I still challenge everybody to prove to me that their AI has really emotional intelligence and not a simulation. And the 4th, that a lot of people forget, which is called metacognition. And only humans have metacognition. That means our ability to have self-reflection imagination and create from zero data something new. Just like Bach could create from absolutely nothing a genius type then of music, ballets. Only humans have that ability. And AGI would need to have those 4 types of natural intelligence to truly be an AGI. So in my personal humble opinion, we're not there yet. So once we were moving back and say, okay, well, I still want my kit, and I created my first kid, Addy, and if you Google me with academia, you're gonna see my selfie with Addy. Yeah, that's my little kid behind. But all he could do is drive very well, or even better than any human. He could not make me coffee. He could not become my best friend. He could not go shopping with me. So how do I bring a particular intelligent machine to be able to be multimodal like a human? And that's when the main area came out to me. Well, we don't have the technology yet for that. So then I left the Volkswagen Group and created QubitNexus.ai with my husband. We're completely self-funded. And we put all our energy and all our particular bootstrap funds into creating that new technology. And we look at quantum computing and thermal computing. And that's where I come now to the next 10 years. The next 10 minutes, the next 23 years. And I'd like then to explain you all what quantum computing is. Because beware of any startup or company that tells you, invest in my quantum computing systems, you don't need to understand the technology, or it's too complex for any person to understand it. And that's why I like to quote Einstein, that anyone cannot explain complex things in simple terms is really the one that doesn't understand it. And just bear with me. I'm going to make you all to understand how quantum computers and thermal computers work. So the computers that we have right now, they were invented by von Neumann in 1945. So that's why it's my first challenge when everyone says an AGI. How can you have an AGI if you're using an architectural system from 1945? That means it just goes to one cycle, one particular task after another in a clock, and after it executes that, stores it, and it stays there, and it goes into the next task. So that means that to calculate prime numbers, m plus m, all of them, it would take even all HPCs in the world, millennia, to be able to do that task. But quantum computers are able to do that within just a couple of hours. So how does that work? Because quantum computers have both states, the zeros and ones, always at the same time. So how does this work? You all know, power, no power, yeah? Power 1, no power 0. And quantum computers, think of it like if you have a coin spinning, yeah? And it has both, yeah, tails and heads at the same time. And we have 2 types, cryogenic, that means absolute zero, and room temperature. And both you can have either photonic based, and that means we use a particular system that makes those photons become a wave through electrical stimulation, and then they are able then to spin, and then they come through something that we call a squeezer, like an orange, yeah? And we're able then to use what would be Bayesian mathematics to know more or less where they are. Yeah? But it's still what we say then in German, more or less calculation, but 70% accurate. But it's still not sustainable. So we have the same type also in room temperature, which uses a different principle. We use then fiber optic cables. And there's also superconducting base. That means they stimulate the electrons on a superconducting metal, and also room temperature base. But the problem is in that case is that they're not as stable. So how does it work? Imagine that you are all looking at each other at the same time, right now. So all of you have a particular thought at this moment. That's what would be then how the basic structurization of a quantum computer works. Then the second thing is that they all connect each other with something called entanglement. And to explain your entanglement, what I want you to do is an exercise, so that you don't fall asleep. So please turn to the person next to you and smile at them, and say hello. Yeah, you all did that? Now please close your eyes. Can you all see that person smiling at you now? Please raise your hand. Yes? Okay, the ones that did, you're entangled with each other forever. That means the ability of one photon particle with another photon particle to become connected to each other. And some of you will go back to London, and maybe you come back to, Germany and Switzerland, and close your eyes and see that face tomorrow. And it doesn't matter where you are, you're still connected. That is entanglement for you. But the next thing that we do is, because there is the situation that you need an observer to understand how it's working, as we call decoherence. That means it's improbable to know the state it will fall, if it will be a 0 and a 1, if they're both spinning at the same time. Okay? What we're doing is the calculation of where that coin is going to fall. So if there is just a small vibration or just a small twitch, then that particular measurement would be wrong, which is one of the limitations of quantum computers that make them still what would be not viable for everyone to have them, apart that they're very expensive, because millions of US dollars. And the other one is that they're pretty prone to errors. So how do we get the errors out of them? And we have something that is called quantum Fourier transformation. And that is that we denoise all the wrongs. Think about it as if I make a wrong calculation, and then Bern is correcting me, and then Annika is also correcting me. And then because I have 2 points of correction, then I can infer I am wrong. Yeah? So it is then double diverse validation, and which is the way that we're able to find out error states in quantum computers. And a lot of people ask me, well, what is the point about this? Can we watch YouTube on a quantum computer? My daughter asked me that last time. And I said, no, that would be a waste of time. And that's not the use case that we need them for. One gentleman was saying, we need computer power, we need performance for calculation for simulations. Well, that's exactly what they're very good for. Quantum computers have no memory. So we still need a hybrid architecture when we're doing this analysis. The HPCs create a digital twin of exactly the architecture of the quantum computers, be it cryogenic or room temperature, and at the same time stores all the data that is fed into it, and then reads all the data back. But the good thing is that quantum computers can create all n plus m synthetic data in simulations that will take our conventional computers millennia to do. And we can do that within an hour. So that's one very good use case that we can use. I just learned right now, also for agriculture. But we've been doing research for life sciences, for banking, for retail and media. And the other thing is for cyber security protection. Quantum computers right now are of the size of what we call 100 qubits. I already explained you, a qubit is the ability to have both states at the same time. And 100 qubits is the equivalent of 1.2 trillion petabytes. What does that mean? Our brain has a storage of 2.5 petabytes. That's 300 million hours of movies. Yeah? So one brain. And one quantum computer can execute 1.2 trillion of that. That's more than data exists in the planet. So imagine the capacity of all the simulations that you could do if you were using that on a quantum computer. But then again, they have no memory, so we still need the HPC data centers outside in order then to process and understand and create the validation and the quality control for it. But they are very good at that. And in the case of the sociopolitical situation that we have, we see that wars have evolved from the typical, what would be use of weapons, sending soldiers, send a plane throwing bombs, into cyber wars. And we're able then to see it now. And we see there's countries, for example, that China, that have opened access to their quantum computers as an open source free service over the cloud. So if a quantum computer can break two-factor authentication in 10 minutes, it can break the particular cryptography of Bitcoin within an hour. That means anyone has got here a crypto wallet, it's no longer safe to a quantum computing, post-quantum computer attack. So they can destabilize financial systems. So that's why it's important, and that's why I'm trying to make awareness here to you, that everyone in every single country and company to prepare this strategy for the post-quantum cryptography era, that it is in 3 years from now. America, in the World Economic Forum, I was there when IONIQ, IBM, etc. say, we will have stable quantum computers, that means 97.9% having a recall stability. So accuracy in a model is the overall quality. Recall is, I give it 1 + 1 and it gives me 2, even though I give that question, that prompt, a million times. That means the ability to have the reliability of the answer. And they say they have that in 2029. That's 3 years from now. So if Europe doesn't prepare now, if Africa doesn't prepare now, if Asia doesn't prepare now, we are already living what I call the digital colonization of America. What do you think will happen if the current administration tells Silicon Valley, shut down Excel, shut down Microsoft, shut down AWS? Our financial systems in Europe, Africa, and Asia will collapse and will create a socio-economical and complete catastrophic chaos within our society, leading even to civil war in certain areas of the planet. We have the digital colonization. So we need to come and become digital sovereign. And that's why in the mission of also QubitNexus. So we're not going public, we don't go for investors because we want to remain neutral, as Switzerland is, to be able to create digital sovereignty through creating hardware and software that's Swiss, that's European, that's for Asian, has an access based on ethical principles. And ethical principles we define the UN Charter of Human Rights, Women's Rights, Children's Rights, in order to be able to give us a chance on the quantum race versus America. So that is one of the areas in that I'm proud that Switzerland treats this very seriously. They're opening a gigantic investment center in Basel with several institutions and other startups too, in order to be able to prepare the next 3 to 5 years for that. Is your country doing that? Please go back and ask, for the sake of all of you. How many of you know how a thermal computer looks like? So they work with something called phonons. And what is the advantages of it? When this gets hot, I cannot call, I cannot use the internet, I have to put it in a fridge so I'm able to call, particularly when I'm in really warm weather countries. So why not use thermal capacity for computing? So how does that work? That means high temperature is a 1, low temperature is a 0. We have around good 70% of the Earth's geolocations now are being affected by global warming or not having enough water. We see it right now, the UAE, they're struggling to explain their citizens why they should still be using water to power their data centers for cyber defense instead of giving them water. So wouldn't thermal computers make sense in those countries in which actually cooling is a matter of water resources, it's a matter of human stability and even human survival? So the way it works, and I wish I could show you, it's, think about like a big UFO, yeah? And it uses, again, the phonons, which is the stimulation of what would be thermal particles. And we have different tubes that serve as an insulator. And the insulators is what stops the processes. And we have different thermal sensors in order to measure high temperature 1 or low temperature 0. It's still at a very early stage, but I think we need to be able to be open to new types of computer and new type of technology. If we want to go into what it is, or the future that I wish I have. And I always like to comment it and put it into two. I want Star Trek, not Terminator 2. And what does Star Trek means? Star Trek means, even though there's so many moguls across the pond saying AI is going to take everybody's jobs, we need UBI, Universal Basic Income, I challenge them and I say, well, with every single industrial revolution that was said, when James Watt created the steam machine, a lot of people in factories, they protested and say, steam machine took our jobs. Second industrial revolution. Yeah? When Volta created the basics for electricity, and then we had electrical machines in factories, a lot of people lost their jobs. The car came over, and what would be horse coach riders also lost their job. And they even say, nobody's going to be able to have a car. Car will never be the most popular form of transformation. So that is just an example. And for those who remember the dot-com bubble, with every new industrial revolution, that was the internet revolution, there's always someone coming up and giving alarmism. And what I want to offer you and give a call for action, let's not do alarmism. Let's create the particular new type of roles, new type of jobs for the particular new technology of the futures. I'm looking for talent, multidisciplinary people that are philosophers, that are physicists, that are software engineers, computer engineers, material scientists, mathematicians, and other areas of science, and also not just engineering science, but also social science to create the new human-centered technology so that we have the Star Trek future and not Terminator 2. Thank you very much.
Thank you so much, Dr. Kathrin Kind.